then they can get started on their research right away rather than wade through all the literature and acquire that stuff. Because although there's a lot of literature, it's not easy to extract the relevant parts in a short amount of time. So often, even I had to just work out a lot of things. It's faster than going through all the literature. But you need to know what the basic aim of the project is, and to know what to look for, because the literature is very big. So first of all, let me clarify. People ask me when they hear the word exact, they want to know what is exact about this. So the point is that usually when you do a renormalization group, what you do is you start with some action or Hamiltonian, then you integrate out or coarse grain the Hamiltonian so that the short distance features are somehow made less important, and the main features, which is the long distance features, are brought out. And usually in this step of going from one Hamiltonian to the lower energy Hamiltonian, there's a coarse graining, which means you reorganize the information and throw away some information. So you go from some Hamiltonian H1 or action H1 to H2, and you throw away information because you think it's not important. So this process is not reversible, because you can't go from H2 to H1. But in the exact RG, the mathematical operation of going from here to here does not throw away any information. Okay, it keeps all the information. It just reorganizes it so that the information that you don't necessarily want is in some, let's say, some higher order term. But in principle, all the information is there. Of course, once you have these equations, your computing power is finite, so you're not going to be able to use all of it. So you'll have to make approximations. At that point, you will throw it away. But the mathematical transformation that takes you in this direction is exact. So you can just go back up or down. So it's in that sense that it's exact, which is not the usual, well, common applications of RG. This mathematical operation itself throws away information right at that step. Here we don't do that. So it's in that sense it's exact. The terminology is due to Wilson, because he's the one who wrote down first exact RG. So the immediate motivation for, at least for me, was there's this connection between exact RG and holographic RG that you can make, and there were some technical issues in that which were not clear. So I found myself reading up some of the literature on that, and that I thought would be useful for the students, so I thought I'd collect that information in the form of a few lectures. Okay. So let me write down a few points. So well, maybe I should just list the main topics that are going to be covered. One is, so this is the equation that Wilson wrote down. The second thing is a different version of this, more suited for perturbation theory. This is written by Polchinski and is often called Polchinski's RG, exact RG. But they're actually related. It's not very different, but this is more convenient when you're doing perturbation theory, and this doesn't use that much. And then I'll talk about how you solve these equations. By solve, I don't mean write down a full solution, but write down an integral representation of this, which will explain some of the features. Then I'll talk a little bit about the notion of composite operators. So this is again a topic that when you study field theory you use it, but when it's usually discussed in the context of renormalization theory, where you have divergences and how you renormalize away those divergences. Here it's a little more systematic treatment in this. I mean, it's easier to, conceptually easier to define it in this context. And the last topic I'll talk about is fixed points of the RG and anomalous, and the issue of anomalous dimensions. Okay, so this is the scope. As I said, there are a lot of things, and I'm going to talk entirely about about scalar field theories. So the whole topic of gauge theories and everything is not going to be discussed here. This is a lot, how you implement symmetries, etc. is not going to be discussed. So this is it. Okay, so one point about the, let me write down the points so that I keep track of them. I said it's a reversible process, and that's what makes it exact. So the crucial point that makes it reversible is that the cutoff procedure is analytic. Okay. So typically you use UV cutoffs which have that kind of behavior, which is a nice smooth function, and you don't lose information when you use that. Okay. That's the first point. So this has to do with the issue of why, one of the reasons why this calculation is exact. I mean, the mathematical equation is exact. The second point I want to make is you have to keep in mind the basic point that what you're interested in calculating are correlation functions. Those are the things you want to calculate, and you're going to calculate, B stands for the Baire. So you start with some Baire theory which you're given, which is your God-given action, and you have some scalar fields and you calculate these correlation functions. So the information that you want to get is this. So you should keep that at the back of your mind, that at the end of the day you should be able to recover that information. And the claim is that you will go down in energy to some other action with some parameter lambda, which is a movable scale. This will be called, I'll describe, this can be called the Wilson action, but that terminology will come later. But the point is, you will go to a lower energy action here, and you will calculate correlations in this. You will calculate correlations with this action, and given this, you should be able to recover that. Okay, so you should be able to go from here to here without any loss of information, and we'll show how the exact RG does that. Of course, as I keep emphasizing, when you actually do a calculation, you have finite computing power, so you're going to make approximations, so you will obviously throw away information. But in principle, you have this behavior of going to low energies, but yet all the information is there in the low energy action. Second point, this operation, how do you go from this action to this action? There are two ways to think about it. One way is to integrate out fields. Integrate out the high energy modes. So if you're working in momentum space, your scalar field has modes with all momenta ranging from 0 to essentially infinity. Of course, you'll put your Baire theory, let us say, is defined with some UV cutoff. So I'll put a UV cutoff here. And then what I'm going to do is I'm going to integrate out modes from lambda naught to some distance here, and look at the action at lower energies. So this is one way of going from SB to S lambda. So you go down in scale from lambda naught to lambda, integrate out all modes of the form lambda less than p. So all these phi p's with this range of p's are integrated out of your action, and that gives you S lambda. That's one way of thinking about it. The other way, or write down a differential equation that implements this. Okay, you instead of doing this integration, you write down a differential equation that takes you from this action to this action, or this correlation to this correlation, and that's what the renormalization group equation is. It gives you a differential equation, and you solve the differential equation instead of doing this integral. Okay. Both are equivalent if you keep all the information, and both are equally hard or equally easy depending on how you organize your calculation. But in this, we'll talk about both ideas, and both of them can be done either exactly or approximately in the sense of being reversible. Now there's an issue. I use the word UV cutoff here. So this is again a source of confusion if you're not followed the literature. Is lambda, this lambda here, UV cutoff or an IR cutoff? So it depends on what your perspective is. So let me say one word about that, because we'll come back. So these are points that you have to keep in mind. So you have your theory at lambda. So you have S bare with some fields and a cutoff lambda naught, and you go down by integrating out fields to S lambda, which has a cutoff lambda. What is this? What is the phi here? The phi here has only modes. This p is typically less than lambda because you integrated out the high momentum modes. Okay, so from the so this is, let's say, p equals 0. So for this is like an effect for the person sitting at low energies. This is like an effective action in which the p is always less than lambda. So this is an effective action. Your physics is cut off by the scale lambda, and this is the action you work with. So when you use this action in your integrals, you have to cut it off at that lambda, because this has only p less than lambda. Yeah.
In reality, the B also is kind of an effective action where all the modes above lambda 0 are infinity.
Yeah. So in the end, we'd like to take lambda 0 to infinity, but that's a different story. Yeah, but you're right. But I just want to make a point here that, so from the point of view of this theory, this is a UV cutoff. But when you're thinking of this theory, what is the process of integration you've done? You integrated out all these modes, and in this integration process, you integrate modes from lambda less than p less than lambda naught. Okay. So now when you integrate out modes, of course what you do is you don't want to lose all the, how do you keep, if you integrate out everything, you just end up with a number. So you don't obviously want to integrate out everything. You have to keep some information. How do you do that? You add a source, right? So if you integrate out all the fields, you just get a number. That's not very useful. So you get it as a function of the source j, which you wiggle around and get your correlation functions. So when you do this integral, you will calculate some generating functional. Okay? In that generating functional, the integrals are done from lambda naught to lambda. So from the point of view of that generating functional, this is a IR cutoff. So what you're actually changing from that point of view is you're lowering this. You're lowering your IR cutoff, and what you would like to do is to take lambda all the way to 0. And you get back your full theory. So depending on whether you're looking at it from the point of view of this person or the person who's working with that, you can think of it either way. Both are, depends on the viewpoint. But mathematically, this is what you're going to do. And the last point I want, I missed one point. So I already talked about things. There are basically three things of interest. One is called this Wilson action. Well, there are actually many things you can define, but the other is generating function that I just defined. We'll define this more precisely later on. And the third thing you can define is the effective action that reproduces the one particle irreducible graphs. Okay. So these are typically three things that people work with, and it's a matter of convenience which one you use. So most of the time I'll be talking about these two, but if I get time I'll mention a little bit about this also. They all contain the same information. For different purposes, different things are useful. And the last point I think I already mentioned is that what you're interested in finally are these guys. This is what you want finally. So through all this formalism, what you have to keep at the back of your mind is this is the object that you're interested in, correlation functions. So if you can get that whatever you do, then you're okay. So these are some introductory points. Any questions about this? Yeah. Yeah. Yes. Yes. Yeah, so again depends on what you mean by integrated out. If you do it with an analytical cutoff, then in principle all that information is there. Yeah, right.
Sorry, can I?
Yes. Yeah, yes.
You might be interested in correlation functions like the low energy effect.
No, I don't mean, well, yeah, I mean you're right. What is this? This is your theory. You have a theory. And all I'm saying is you're interested in the correlation functions of that theory. How you compute that theory is up to you. But ultimately this is your theory. This defines a theory. Whether you compute it using SB or with S lambda, that's your choice. But this is the thing you should be able to recover. This is the original.
Then one more slide.
Yeah.
So that SB depending on lambda naught.
Yes.
The renormalizable theory, there is no explicit dependence on any scale in SB, right?
Well, if it's an exactly marginal thing, it will not. But at the quantum level, you will have to introduce a lambda naught. So as soon as so there is an issue of how you take lambda naught goes to infinity. So for some purposes. So for instance, if you're working on in the context of statistical mechanics or condensed matter system, this lambda naught would be the lattice of the microscopic lattice. It's just there, it's not to be taken to infinity. In a field theory, you would want to take lambda naught to infinity. So if you want to take lambda naught to infinity, there'll be some further restrictions on what actions are allowed. Not any action is okay. So that's an additional restriction you have to worry about. But all this process assumes that there is some SB you're starting with. And what do you do with that? Okay.
It's already your starting point is with some lambda naught.
Some lambda naught, yes.
Like a lattice regularity.
Yes, yeah.
So you can
But that lambda naught, you can pretend that you're going to take it to infinity.
in which case you might get a continuum.
In which case you get a continuum theory. Yeah. So
Think of it already as some regularized action. Starting.
yes, but we will take that lambda naught much larger than any scale of interest. So you will actually be studying. This will be your moving scale. So all objects which are down by powers of lambda naught, for the purpose of this, you can throw away because you're going to assume that a continuum theory exists for the particle physicist, and that you can take lambda naught to infinity. That's of course something you have to verify a posteriori.
You might have thrown away information in getting to SB from that continuum.
Yes, yeah. So of course, if you define your SB as the correct theory at very high scales, then hopefully all the information is there. Yeah. No, that's something you have to worry about. So with this background, I'm going to start writing down that equation. So I'll work out some of the algebra because this is supposed to be like a course, not a seminar. So I'll write down the first, let me write down the equation. So here's the equation that Wilson first wrote down. While you stare at that, let me erase this also. So this is some kind of a diffusion equation, and he wrote this as a model. So what he wanted for this wave function, this looks like a wave function, psi prime is, he took it as some kind of e to the power of minus Hamiltonian, or if you're working in Euclidean field theory, it's the Euclidean action, whatever you want. Okay. So we'll be working with equations of this type several times in these lectures. So let me just indicate one simple way to, there are many ways to solve it. I'll just indicate one simple way to solve it, which is to, well, so I should say that this equation was his prototype equation which implements this RG transformation. So we should understand the solution. So this one simple way to do it is to map it to a simpler equation by the following mapping. So you change variables from xt to y tau, just do a change of variables. X, sorry?
What is x?
Oh, this psi is a function of x and t. Yeah, so this, you can think of it as a zero-dimensional field theory if you want at this point. It will become the fields later on. So you change variables. In fact, I'll do that in a minute. Yeah. So you'll go from a wave function as a function of x and t to some wave function as a function of y and tau. And actually, for convenience, it's also convenient to rescale this. So you will write psi prime. This is not very important, this factor, but we'll bring that. So I'll just change a variable. So this will give you. So this is.
Are x and t like a length and time variable, or I'm supposed to think of it just dimensionless?
No, here it's just two variables. Later on, x will become the field, t will become the RG scale. We'll see that in the next step. We'll see that. I mean, not immediately after this. We'll see that. So d by dy. So I'll just do an elementary step of the algebra for, because these kind of transformations we'll keep doing. So this will give you, because this is 0, so this brings in that scale factor. So again, I didn't write down, sorry, I didn't write down the transformation. Y equals x e to the power of t by 2 and tau equals e to the power of t. Okay, so this is the transformation. This transformation is fairly typical of what happens in RG. This is, if you think of this as a field, this is like a scaling, okay, with some time. So immediately, of course, d squared by dy squared is e to the power of minus t d squared by dx squared. That's straightforward. But because of the time dependence here, this transformation changes. D psi by dt gets an extra piece. It gets a piece so this becomes half y dy so you notice that the time derivative has also a space derivative. This is also a typical feature that happens in RG. So your left hand side will now involve this, so your equation is going to get modified. So you plug all this in. Now you can just plug it into that and see what you get, and what you get will be the following. This equation, so this equation will get mapped to the following equation, which you'll recognize very well. Simple equation for which this is just Schrodinger's equation with the I taken away, so it's a diffusion equation. And this ever since Feynman wrote down the solution, we know what the solution of this is, at least the integral representation. You can write it like this, psi this is Feynman's solution. Okay, if you take away the I. Yeah.
Let's say whatever the first equation that we're taking.
This one.
Is the derivation for this or it is just something which is postulated?
Oh, this one. Oh, he postulated this equation because it has interesting properties. The solution looks interesting.
Nothing to do with any transformation, component transformation?
Not directly, but you'll see what it does. It implements a coarse graining. That's what I'm going to show you. A coarse graining. So
this was just an equation that
he wrote down, yeah. And in a minute we'll generalize this to field theory. So this is the solution for y, and so the point of this mapping is just to tell you that this equation you know and its solution you know. So all I have to do is to go back to my original variables and I get the solution to that. And the solution to that is the following. So of course I could have skipped all this and just given you the solution, but I thought it's useful to see how it comes. If you just do this go back to the original variables, replace tau by and t by these variables, you will get the solution I'm going to write down. Of course, overall constants, this is of something like this. So if I have some overall constant like 2 or 3, it's not important. It's just only the things that depend on x are important. Okay. So I'm not worrying about some overall factors of 2 or 3 or something. So the solution is like this, half xf minus so this is the solution of this equation. And now you'll see that it has an interesting property. What is that property? Look at the behavior as, so you start with some initial state, function of xi at initial time ti, evolve, you get some final state as a function of xf and tf. But remember that what you're calling a state or wave function is just e to the power of minus that. Okay. So study the limits. And tf goes to infinity. Okay. So when tf, or I should say tf goes to ti, because initial time is 0. So when tf goes to ti, this becomes 1. So this denominator goes to 0. So this basically becomes a delta function, because so xf is forced to be equal to, this becomes 1, xf becomes forced to equal to xi. So when tf goes to ti, this whole thing becomes a delta function, and up to some normalization, this fact in fact guarantees that the integral is 1. So your psi xf tf actually is the same as this. So psi xf tf, so maybe I should call this the call this initial wave function, this is the final wave function. So psi of fx ti is exactly, it's the same wave function, the form is the same.
Sorry, the 1 minus Tm minus Tm, the exponent.
This whole thing is an exponent. Yeah, see, it's just this thing. This thing has been mapped into that, but because it's an exponential. So in that limit it becomes a delta function, as it should. So you haven't, and tf goes to 2i, there's no evolution, so you recover your original wave function. What happens when tf goes to infinity? this has a factor e to the power of minus tf, so this drops out, and this integrand, this kernel, has no dependence on xi. Okay, so you end up getting basically a Gaussian times the integral dxi of your initial wave function. So this is a crucial point. Crucial point, why? Because as tf goes to infinity, your final wave function is a Gaussian, independent of what your initial wave function was. So this field xi is completely integrated out. Okay. So all information about your initial wave function is lost. Your final wave function is just a Gaussian. So this is, so as you vary from tf varies from ti to infinity, you are integrating out more and more the fields or the x's in the original wave function. You start with having complete information to no information. So this was his idea. So he said, let's now do this in the field theory, where you define some variable that as you go from 0 to infinity, it integrates out different modes. But of course, what you want to do in the RG is you don't want to integrate out all the modes uniformly. You want to integrate out the high MNT modes. So now I'm going to make everything a function of field. So my x will actually be a function of p. So you think of every momentum mode of your field theory as a coordinate, and label it by a p. Whether it's discrete or continuous is not important, it's some function of p. What you would like in the RG is that as you evolve in time, the high values of p should get integrated out faster, and the low values of p should remain untouched till the end. So you want your function somehow to depend on p. So you want this time somehow not to be the same for all p, but it should depend on p. Okay. So to that end, he wrote down the following obvious generalization. So define, instead of time, you define a functional of, what did I call it? I call it g. I think in his original paper he called it alpha, g of p and t. Instead of replaces t. Of course, I could have just made this t into a function of p, but I choose to call it g and keep a label t, which just as a parameter. But what will the time variable for any given mode will be this. Okay. So let's write down the analog of this equation, with t being replaced by that g and x being replaced by x of p. So he wrote down the following equation. Now it's a functional because it's a function of p. So this function is now a functional of x of p, and you can put the g inside here if you want. So we just write down the same equation as there. So delta by del x of p this is a straightforward generalization of that. And you can write down the solution of this, just put the p's everywhere, and the solution is, instead of solution, it's better to say it's an integral kernel representation. So what do you get? Just replace that xf of p, and you can call it g of p and g, or g, let's call it gf. Or maybe I'll just call it g of, let me call it gf as g of p and df. This is d of, so now instead of ordinary d, I'm using this curly d to indicate that it's a functional integral. Df, and then the whole exponent is the same as before, minus half. So what goes here is, there's an integral over p. So this is your d diamond d dp by 2 pi to the power of d, etc. So okay. G of p and t minus g of p and 0 times xi of p. Actually, I've used, instead of ti and tf, I've used 0 and t. Okay, so 0 is your ti and t is your tf. And then the same thing with p replaced by minus p. Same factor. So this is that, this factor is just this part squared divided by, this is all in the exponent, 1 minus times psi of, so you can call this the initial time. It's exactly, so I call this xi. So it's just the functional version of that. Okay. So this will implement an integration out of the various modes if you choose this gf appropriately. What should, g appropriately. So you have to choose g. It should increase with p squared or p for any given t. So at any parameter time t, the g should be larger for the high momentum modes than for the low momentum modes, because those are the ones you want to integrate out first. Okay. So here's the GP that Wilson chose. Okay. So it this is some overall constant factor. So there is no p squared dependence, it is like this e to the power of t, similar to that. Then this is the p squared dependent part. So as the larger the p squared is, the larger g is. So the high values of p are integrated out faster, because this goes as p squared. Okay. So as, yeah. Huh? P is this, because everything is a function of p, right? So these are fields now. So what you normally call phi of p, I'm calling x of p. The reason I'm calling it x of p is because these equations are very easy to visualize, solutions and all that. So whenever I write down an equation like that, I'll just drop the p dependence and it'll look like an equation like this, which you can solve very easily. So what is the differential equation corresponding to this? We had a functional differential equation, but you can write this as a time derivative. So let me erase this now. So you can convert this equation to a more to the following equation, which you can show is the same. So you think of writing delta psi, take delta g to that side, differentiate the whole thing with respect to t, and you'll get a g dot. So you'll see this, what I'm going to write down here. more conventional form, you can see this is equivalent to that, because if I think of this as delta g by delta t, then this cancel out the dt's and you bring the delta g here, you get back your functional differential equation. Okay. So this is equivalent. So this is the equation that Wilson wrote down, and he called it the exact RG equation. Okay. So we will deal with other equations of this type, but to solve it you realize it's a functional equation, so it's actually a collection of an infinite number of ordinary differential equations or partial differential equations, and you can make various approximation schemes to solve this. Okay. So this is just a quick introduction. This is a quick derivation of Wilson's equation. Of course, now if you put back psi equals that into this equation, then your equation looks like the following. So now I've dropped the p. If you just drop the p's, this is much faster to write down. So you can put back all the p's and put an integral sign whenever you want. So this will become So this is very similar to the original equation, except I have this factor. So, right, except for this factor, and if you write it in terms of the s, this equation becomes ds by dt Okay. So once again, I have simplified the notation. All these are actually functional. So for instance, this term in the field theory would be d squared s by dxp dx minus p, and this one would be ds by dxp ds by dx minus p, etc. And then you will have to put a integral over p. But other than that, it's the same equation. So this is also called Wilson's equation. In fact, that's the way it's usually used. Here you see the nonlinearity, because this is the action. This involves product of two actions, so it's a nonlinear term, whereas here it looks completely linear. So there's some advantages of this. Okay. So what is it? So to summarize, what we've done is I have written down the original equation that Wilson wrote down, along with given you his motivation, and the motivation is simply that you're in the process of evolving this t, you're integrating out the high momentum degrees of freedom faster than the low momentum degrees of freedom. So that is the RG operation, and because it's written as a differential equation, you can just reverse it. As you can see, there's no information lost. Information would be lost if you use some sharp cutoffs here. I mean, if this is some non-analytic function, then it would be hard to integrate it back, go back in time. But as it stands, it's completely reversible. So what I want to show you next is, yeah.
So the solution now depends on what function you choose for g. Right? So
Yes.
depending on different
Yes.
values, you have different kind of
Equations.
equations,
Yeah.
and also the integrated out theories will depend on what.
Yes, yes, yes. So ultimately, the idea is that when you're near some fixed point, those things will become unimportant. But yeah, so in fact, Polchinski's equation will be different from this equation. But the idea that your coarse graining will be there in all these equations. So that's, but I mean that's as you should be, RG, there's nothing universal about the coarse graining procedure. You can use any procedure you want.
What is the argument that led to this particular equation? It's like God-given equation.
No, I think.
That it's going to give us some expressions.
Yeah, I think these equations are known. These equations are known to people who study diffusion. These are called diffusion equations. So he probably is. I mean, people have seen these solutions, and I derived it for you via this. But
okay, so there is some kind of
there's a
type of
yes,
picture that is assumed.
that's right. Yes. No, he's not assuming it. He's just saying this equation has this solutions that has the right behavior that you want for an RG. The fact that these equations have been used in diffusion theory is an independent fact. Right. Yeah.
But it should be obtainable by the argument where you have integrated out some.
Yes. Yeah. So I will. So what I'll do is I will do that. I'll talk about that in a minute. I will, instead of doing it for this equation, I'll do it for a slightly different equation which is related to this, and that will be Polchinski's equation, which is related to this. But there you will see the integrating out much easier, much better. But before I do that, I want to show you the main point that I keep making, which is that from a solution of this equation, you should be able to recover the original correlation functions. So let me just show you that. So I'm going to erase this. Yeah.
We are interested in the low energy fields.
Yes.
So these are all going to lead to different low energy depending on what G and things.
Yes.
So which one is the correct one for this problem?
Well, it's not okay. So there are some there are some features which are generic and some features which are very specific. So since you asked that question, the choice of the C has some specific information about what theory you're going to go towards. So in fact, this will have information about the anomalous dimensions, etc. So if you go to some fixed, if you want to go to some fixed point for which the scalar field has some anomalous dimension, that has to be put in there. If you put in some other anomalous dimension, you'll likely go into some other fixed point. Or if there's no fixed point, this equation won't have sensible solutions. So to a certain extent, this is a generic equation. Having a good solution depends on some good choice of G. This part is not so important. It just differentiates the high momentum from the low momentum. You can put other functions. It won't change that. It should be such that the high momentum modes are suppressed compared to in the low energy theory. So when we study specific equations, especially when I talk about the fixed points and anomalous dimensions, you'll see this coming in.
So there looks like there is a class of maybe marginal theories for which the p-squared piece is not important. But if you're looking
No, that p-squared
some
piece.
other class of theories that might be important.
No, the p-squared piece is actually implementing. Well, maybe you'll see it better in Polchinski's form. It just implements the fact that there's a UV cutoff. That's all it is. It's implementing the fact that your low energy modes are not affected by that, are not integrated out, whereas the high momentum modes are integrated out fast. So your low energy theory is convergent. Yeah, because these are very. It's like it'll turn out to be like an exponential. It's like a Gaussian cutoff. So any polynomial theory will be. I mean, if you start with an action which is e to the power of plus p squared, then you'll be in trouble. But otherwise. So remember this psi is like a action. So let's consider so now I'm switching gears a little bit. This is a transformation I'm going to make, but I'm going to use conventional field theory language now and write this, but in the same notation. So let me call it dxf. So remember, xf was the field degrees of freedom you got at the low energy theory. So this is the low energy, this is the field variable in the low energy action, and xi are the field variables in the high energy action. So I'll just call it high energy variables or high energy action. To the extent that these are just variables of integration, it doesn't matter what you are, but that's the way they the point is this enters the low energy action, high energy action, that enters the low energy action. But of course it's just a dummy variable that you're going to integrate over. So here you're integrating over that. So this, suppose you get this low energy action, which I will call F, and then I want to calculate correlation function, so I add the source. So this is the action you get after you've done the RG. So your psi of xf, this is your psi of xf. Okay. So I haven't yet made precise what t is, but it will come later that t is related to the scale, the lambda, the scale lambda. Okay. So this is your low energy theory. And how do I calculate correlation functions? I do this. You can use an x or p, it doesn't matter. Since I'm working in momentum space, it's better to take p. So this is the correlation you calculate from S, the low energy action. And you can put higher derivatives and calculate higher ones. So let's write S in terms of the other one. So we have that solution there. So your solution is of this type, e to the power of minus s xf. I'll just explain in a minute what all these are. So what I've done is I've just rewritten this solution, calling this thing as z and the coefficient below as a, 1 over a. This is the general form of the solution. It's some Gaussian xf minus xi with some factor. This factor is at e to the power of g factor multiplied by something, the denominator which I'm calling that. Remember that all these are functions of p. So this is what your Sxf is. So what I would like to do is to use this equation to relate these correlations to the correlations that you would use with calculating from that. Okay. So that's what I'm going to do now. So I will erase this equation, so I don't need that. So let me now substitute this expression in there. So substitute. So we'll call this 2 and this 1. Substitute 2 in 1. So you will get z equals dxfp dxip. So this is dummy variables in e to the power of minus half p so I'm going to I'm going to condense all this into that, You put back all the p's later. So this is what you get if you put this into that. Okay. I've just substituted for SF all this. So there's an additional integration over xi. So we'll take out the xi part now, right? This is dxi. So you can call this Si, by the way, and this is your Si, and this is your SF. Exi times do the rest of the integral dxf. So this whole thing a squared xf minus zxi whole squared plus, so we're going to change variables. I'm going to integrate over xf, so I'll call this whole thing x prime. It's just a variable of integration. So this part will become dx prime p e to the power of minus half a squared x prime squared. Again, x prime squared means x prime p, x prime minus p, integral over p, etc. Plus this j now I replace in terms of, so xf minus zxi is x prime, so xf is x prime plus zxi, so I replace that there. So this becomes jx prime plus jzxi. So just change your variables. Now you can do the x prime integral. Here very easily, right? So notice that the hard part of the field theory part has come out separately and you're just doing the rest of it. So this is equal to dxi what does this give you? This gives you a quadratic term in j with that as the denominator. So you get what, e to the power of half j of p, this is a standard field theory result, minus p by a squared p plus jzxi. So again you had to put all the p's back in, etc. So I have now related, I have my z of j in terms of, now j is the source for xi, okay, and I have the original action si. This is the original action which you can think of as a bare action. Only thing is there is this factor z. Otherwise j is the source for xi just as it was the source for xf. So here it's xf, sorry. So the same j continues to be source for xi except for this factor of z. So now you can calculate these guys and the higher ones. So so this part, that's the conventional generating functional for the xi, okay, except that the source is j times z.
If I scale this at z times x, it's going to be standard form. If I scale z times x, it's y x.
Oh, you can do that, but my point is I'm trying to relate correlation functions of the two theories, so I need to keep that. I mean, yeah, it's an overall scaling. It's your wave function renormalization. It will come back later, so you can scale it if you want, but we have to keep track of that. In the sense, it has some physical effect, but as you say, you can scale it. Yeah. So let's just calculate it. So except for this j by a squared piece, which will affect some 2-point function, you get your original correlation function. So let's just calculate this term. What will you get? So this thing will give you the following thing. It will give you z p1 z p2 xi p1 xi p2 in the original Si plus a delta function piece and if you calculate the cubic one, so you can calculate d cubed z by dj p1 dj p2. I'll just do this also to show you how it works. This cubic one, so this is your quadratic one. So this is what is this equal to? And if you calculate the cubic one, you can just do this. Cubic one, this won't contribute because when you put j equals 0, it will go away. You will just get zp1 zp2 zp3 times xi p1 xi So these are the two relations. So the important point is that there's a precise mathematical connection between the two. So as long as these functions are non-singular and well behaved, you can calculate this from this. Okay, there is this piece, this sort of disconnected piece that you have to subtract out, which is not there in the cubic term. If you calculate the 4-point function, there will be 2 of these, but other than that, the main information is in here, and that is here, and it's just proportional to the z. So as long as your z is an analytic object, this function is analytic, well behaved, all the information is retained. So you can do this for n fields. So all the correlation functions of your original theory are there in the low energy theory. Okay. So which one?
Continual motion.
We know which?
Like, two Green's functions
Ah,
can be related by
yes.
product of wave function around.
Yes. So this, so that's why I deliberately use the notation z. Z will in fact turn out to be the wave function
That
denomination.
could be divergent.
So all that is in the t dependence here. So notice that g has this t in it. So this will actually turn out to be the ratio of the logs. But here you don't have to talk in terms of divergences. It's a very shall I say logical and systematic framework.
Right, this one here is the 2.4.
Yeah, so the first one,
And this last bottom line is that d2z dj squared.
yeah. So this is what, this was this. And the next one is the 3-point. So I've run out of time. What I will do next time, I'll just tell you, is I will do a different version which is more suited for perturbation theory, which is the version that Polchinski wrote down, and that can also more easily be related to this integrating out. Okay. Since I run out of time, I was planning to talk to 3, so maybe yeah, maybe I'll stop here because I won't be able to get very far. Okay.
Sorry, that you're defining